In this video, I'll be solving this minimization LP problem using this simplex tableau structure. One of the solution approaches in solving the minimization problem is to choose the largest negative value on the Cj minus Zj row to enter the basis, rather than the largest positive value as done in maximization problems. Another way is to change this Cj minus Zj to Zj minus Cj. And another way is to convert the minimization problem to a maximization problem by multiplying the objective function by -1. And that's what we'll do in this video. So we will be working with this maximization objective and the constraints will remain the same. The idea is that making cost as small as possible is equivalent to making profit as large as possible. To put this in tableau form, we need the right side of the constraints to be positive. Therefore, we multiply the second constraint by -1 to make its right hand positive, and that also changes the direction of the inequality from a less than to a greater than. The original minimization problem is now equivalent to this maximization one. Writing it in standard form, we introduce a slack variable to the first constraint because it's a less than or equal constraint. We introduce a surplus variable to the second constraint since it's a greater or equal constraint, and the third one does not need a slack or surplus because it already has equality. Based on this model, suppose we make x1, x2, and x3 non-basic by setting them to zeros. We will have s1 equals 18 and s2 equals -14, which poses two problems. First, S2 violates non-negativity, and second, there is no variable representing the equality constraint. These issues prevent us from setting up the initial simplex tableau. To circumvent them, we introduce what we call artificial variables, sometimes denoted by lowercase ai and sometimes by uppercase ai. In other words, we introduce artificial variables whenever we have a greater or equal constraint or we have an equality constraint. Artificial variables are indeed artificial because they have no real meaning in the problem. They are essentially used to set up the initial simplex tableau with a basic feasible solution, and they must be eliminated before we reach an optimal solution. So the equation of the first constraint stays as is. No artificial variable required there. We introduce an artificial variable a2 to constraint 2 equation because it's a greater than or equal constraint. And we introduce another artificial variable a3 to constraint 3 since it's an equality constraint. We denote them a2 and a3 here to match the constraint number. You may prefer them to be a1 and a2 to indicate the first and second artificial variables introduced, but it doesn't matter. Since we don't want the model to keep artificial variables in the solution, we include them in the objective function with a very large negative coefficient or large cost, which we denote -m. Note that m is a large positive number. You can hold a large number in mind like 1 billion, and all variables are non-negative. The problem is now in tableau form. We begin by setting up the tableau with the objective coefficients, followed by the coefficients in the constraints, then their right-hand sides, that we call the B column. The basic variables will be the ones with unit columns, the ones that have a coefficient of 1 in one of their rows, while the coefficients of the other basic variables are zeros on that row. So S1, A2, and A3 will be our initial basic variables, and we'll list the objective coefficients in the CB column here. The Zj values are calculated by taking the sum products of the CB columns and each of the other columns. For the x1 column, we have 0 times 2 plus -m times -1 plus -m times 3, which gives m minus 3m or -2m. For the rest of the columns, because of the 0 here, we can ignore the first row, and because the two coefficients are the same, we can simply add the bottom two coefficients and then multiply the sum by -m. So 1 plus 2 equals 3 times m gives -3m, then -4m, 0, positive m, negative m, and -m. For the B column, -14m, -26m gives -40m. For the Cj minus Zj row, or what we call the net evaluation row, we take the objective coefficient row and minus the Zj row. So 6 minus -2m gives 6 plus 2m. -7 minus -3m gives -7 plus 3m. -4 plus 4m. 0, -m, 0, and 0. We reach the optimal solution when there are no more positive values on this row. This setup is called the initial simplex tableau. The largest positive entry on this net evaluation row determines the new variable entering the basis. Since m is a very large positive number, 4m is larger than 3m or 2m. Therefore, -4 plus 4m is the largest positive value on this row. This x3 column is the key or pivot column, and x3 is the new variable entering the basis. To determine the pivot row, we compute ratios of the B column values to the positive pivot column values. The smallest of these ratios determine the pivot row. If the pivot column has values that are either negative or 0, we will ignore them as we are only interested in non-negative ratios. The first ratio here is 18 over -1, which we will ignore since it produces a negative value. The second ratio is 14 over 2, which gives 7. The third ratio is 26 over 2, which gives 13. The minimum of 7 and 13 is 7. Therefore, the key or pivot row is the second row, and the variable leaving the basis is A2. The value at the intersection of the pivot row and the pivot column, which is 2 in this case, is called the key or pivot element. Moving forward, A2 will be leaving the basis, and because it's an artificial variable which has no real meaning in the solution, it can be removed from the columns altogether. So in the new tableau setup for the first iteration, A2 has been replaced by the pivot column variable x3 with the objective function coefficient -4. We begin this first iteration by dividing the pivot row by the pivot element, which is 2. So -1 divided by 2 gives -0.5, 1 over 2 gives 0.5, 2 over 2 gives 1, 0 over 2 gives 0, -1 over 2 gives -0.5, 0 over 2 gives 0, and 14 over 2 gives 7. Next, we make the initial pivot column a unit column by making all other entries in that column zeros. This is done simply by adding or subtracting a multiple of the pivot row. To make this -1 a 0 in the new tableau, we can easily add it to the 1 here and do the same for the other elements on that row. So 2 plus -0.5 is 1.5, 5 plus 0.5 is 5.5, -1 plus 1 is 0, 1 plus 0 is 1, 0 plus -0.5 is -0.5, 0 plus 0 is 0, and 18 plus 7 is 25. To make this pivot column entry on the third row 0, it is currently 2, we can multiply this new row 2 by 2 and subtract the result from the old row 3. We can also obtain the same result by simply subtracting 2 minus 2 here. In that case, the operation is old row 3 minus old row 2. For the x1 column, 3 minus -1 is 4, 2 minus 1 is 1, 2 minus 2 is 0, 0, 1, and 1. And for the B column, 26 minus 14 gives 12. Next, we compute the entries of the ZJ row using the sum product of CB column and other columns. Since we have 0 in the top CB row, multiplying the top row values by 0 will result in zeros, so we can ignore the first row in calculating the ZJ values. For the x1 column, we have -4 times -0.5 plus -m times 4, which gives 2 minus 4m. Next, -4 times 0.5 plus -m times 1 gives -2 minus -m. Next, we have -4, then 0, 2 minus m, and -m. For the B column, we have -28 minus 12m. For the net evaluation row, 6 minus 2 minus 4m gives 4 plus 4m. -7 minus -2 minus m gives -5 plus m. Then we have 0, 0 again, -2 plus m, and 0. And that completes the first iteration. Remember that m is a large positive number. Thus, the largest positive value on the net evaluation row is 4 plus 4m, indicating that the pivot column is the x1 column, and the entering variable is x1. To determine the pivot row, we calculate the ratios by dividing B column entries by the pivot column entries. 25 over 1.5 is 16.7. We skip the second row since its pivot column entry is negative. We don't want negative ratios. For the third row, we have 12 over 4, which gives 3. The minimum non-negative ratio is 3, indicating that the pivot row is the third row. The variable leaving the basis is A3, and the pivot element is 4. For the next iteration, x1 will replace a3 in the basis, so we can remove a3 from the columns because it is an artificial variable that has served its purpose and is no longer needed in the tableau. Note that we do this only for artificial variables. If a non-artificial variable leaves the basis, it is not removed from the tableau. For the second iteration, we have x1 replacing a3 here with an objective function coefficient of 6. The primary goal again is to make the previous pivot column a unit column. We first make the previous pivot element a 1 by dividing the third row by the pivot element 4. 4 divided by 4 is 1. 1 over 4 is 0.25, 0, 0, 0.25, and 3. To make this 1.5 position 0 in the new tableau, we subtract 1.5 times the new row 3. So 1.5 minus 1.5 times 1 is 0. 5.5 minus 1.5 times 0.25 is 5.125. 0, 1, negative 0.875, and 20.5. And to make this negative 0.50 in the new tableau, we multiply the new row 3 by negative 0.5 and subtract it from the old row 2. That is, we take the old row 2, add 0.5 times the new row 3, and assign the result to the new row 2. So, negative 0.5 plus 0.5 times 1 is 0. 0.5 plus 0.5 times 0.25 is 0.625. 1 plus 0.5 times 0 is 1. We have 0 here. Negative 0.375. And 7 plus 0.5 times 3 is 8.5. For the zj row, we can again ignore the first row since its CB value is 0. Hence for the x1 column, negative 4 times 0 plus 6 times 1 is 6. Negative 4 times 0.625 plus 6 times 0.25 is negative 1. Then we have negative 4, 0, 3, and negative 16. For the net evaluation row, 6 minus 6 is 0. Negative 7 minus negative 1 is negative 6. Then 0, 0, and negative 3. Since there is no positive value in the net evaluation row, the objective function cannot be improved further. So we have an optimal solution given by x1 equals 3, x2 equals 0 since it is non-basic, x3 equals 8.5, s1 equals 20.5, and s2 equals 0 because it is non-basic as well. The objective function value for the maximization problem here appears as negative 16. But since this is a minimization problem, we multiply it by negative 1, and that will give an optimal objective function value of positive 16. And here are some highlighted events in solving this problem. Because the problem was a minimization problem, we multiplied the objective function by negative 1 to convert it to a maximization problem. 2. Because the constraint has a negative right-hand side, we multiplied the constraint by negative 1 to make its right-hand side positive to be suitable for the initial simplex tableau. We added artificial variables to greater than or equal to constraint and to equality constraints, again to make them suitable for the initial simplex tableau. Number 4, we set the coefficient of artificial variables to negative m in the objective function, where m is a large positive number. Number 5, we evaluated the resulting simplex tableau in typical fashion and multiplied the optimal objective function value in the tableau by negative 1 to convert it to a minimization objective value. And that's it. Thanks for watching.